Alright, the first thing that we did when starting this bridge project is we wanted to actually define what our goals and objectives were. Of course, we wanted to maximize the strength to weight ratio for our bridge, but you also want to stay within the dimension specifications. And you wanted to construct a bridge that could be analyzed using the skills that we've learned. We didn't want to do anything outrageous that we couldn't really analyze very well. Yeah, once again, we just kind of sat down and we just kind of went over what could we do, what kind of materials could we use, what kind of dimension, what are our dimension limitations, what can we actually using the materials and our what we have to be able to construct it. We want to do something feasible that wasn't out of the range of possibilities. Of course, as experimental setup, we're all familiar with that. It is to be constructed entirely from balsa wood and any glue that the group prefers. And obviously we need to keep within dimensions, but once again we needed to be practical about what we did. We didn't want to do anything too outrageous. Whenever we sat down to design it originally, we originally designed it to be a K-truss. We researched on the internet and in textbooks, and apparently a K-truss is used very commonly in bridge design. The only thing with this is we actually knew where the load is being applied for our project at the middle, and with K-trusses it's usually for a moving load like a vehicle. So we decided to scrap that idea and just do a regular truss. We ultimately just used our own personal knowledge. We didn't use the K-truss like I said. Really, we kind of did it on the fly whenever we were constructing it. We just kind of decided what we think would make a good bridge. We just drafted a drawing in AutoCAD and used that for our construction, which the drawing I think is next. And that's our drawing from the side.
All right. When designing a bridge, one of the things that you want to analyze after you've come up with a design is how the load's going to transfer through the bridge. Since we knew that the load was going to be applied at the center, we knew that the bridge deck would carry the load to the beams underneath our bridge. And then when analyzing this, these center members have twice the tributary area of the outside members, so they're going to carry twice the load. So we made sure that we doubled these, and then they're more singled on the outside, less glue. So, and then with the top truss, it's mainly there to support in bending. Once it starts to bend, this will start to carry the load, and as this deflects, it'll carry up through these and keep your bridge from bending, make it stiffer, carry more load. So, once we knew that, we could better design the bridge and come up with different design aspects to make it a better bridge design. That's pretty much the same thing that I just said. So, it's all written out. Yeah, I got you.
Alright, I think the materials that we used were obviously balsa wood. We chose Gorilla Glue just because of the strength it had. It wasn't too much more expensive than just regular wood glue. We used a piece of foam board, tacks, wax paper, pocket knife saw, some safety goggles while we're cutting the wood. That's the reason we chose Gorilla Glue. I went all around looking for balsa wood, and I went to Ace and the frame shop downtown is where I ended up buying the wood from. I found our deck, the thick part of it on the bottom. I found that downtown, and I had done a project like this in high schools, and we used 1/8" members, so I kind of had an idea, but I couldn't find too many of the thicker members that the other groups used. So we used the 1/8" members, thinking that it would cut down on the weight of the bridge. Yeah, we ended up doubling the width or thickness of the bottom cord because we figured that would be the one with the most compression. So we made it thicker so it would be able to hold up a little bit better. We chose a thick bridge deck because we figured that would be what would be holding most of our load, especially since the truss part of our bridge has the thin members. We knew that wouldn't be able to hold a lot. And the way we built it, we traced out a full-scale drawing of our truss onto the paper, put wax paper on top of it, and then cut the members to size and put those down and glue them together. It took a good bit to dry with the Gorilla Glue, so we had to think about, plan out how we were going to build it, that way we weren't spending too much time sitting around waiting on the glue to dry. And then we used the tacks just to hold kind of like clamps to hold the pieces in place while we're waiting on them to dry. Yeah, that's one of the problems we ran into, just thinking about how we're going to put it together so we wouldn't be just sitting around wasting time. And it took about 12 hours overall to do the whole thing.
This is a picture of our bridge right after construction, before we had done any loading on it. Obviously you can see the thing there, but all right, and then this is post-test. Actually, I think this one, it was during the loading, but after the loading had begun. You can see right here, these are starting to flex out and resist the buckling. You can certainly see the effects of the compressive loads in those, and then in this figure over here, you can see where that member actually snapped from the compressive load. And this one is a good picture to show how much it deflected. You can see it's not even touching the tool we're using to measure the deflection. And then on the bottom there, you can see how the rollers were sort of shearing that bottom truss system. And this is after it reached maximum deflection when they kept loading. As far as why or how our bridge failed, the first thing to go was, as you saw in the picture, where the bottom truss system was being sheared at the rollers. And once that sort of gave way, the bridge deck was almost just sitting on the supports, and it started to deflect. The more that deflected, the more your truss system began to experience loading. And again, the top members, of course, the top cords received a lot of compressive loads, and they resisted for a while, which gave some good ductile failure, but eventually they began to buckle, and then at that point all the stress was on the actual bridge deck, which continued to deflect. And then after it reached the maximum deflection, because it never actually failed in the sense of breaking, but it did reach the maximum deflection of a ½ inch. And then after that was reached, they continued to load it with a little bit of crack in the bridge deck, but still no real failure. And then this is just about the ductile, how it failed. Ductile, which is actually desirable, because of course you don't want a bridge to be looking fine and the next minute it's broken, and cars are falling in the river. So it's good to have a ductile failure. You have a warning. You can hopefully have time to fix the problems before any catastrophe.
Possible improvements. Just for our bridge, we use really thin members, so using thicker members to obviously hold more strength.
What members should we?
Well, overall, just thickness of our members, just like using thicker ones. But then also
members or the deck or the upper system?
The bottom part.
The bottom part. But then also for our compression members for buckling, we should have doubled those to hold more compression, and then also for the tension ones, we probably didn't need to double those as much as we did the compression members. And also we used a ton of glue that we could have cut down on to reduce the weight. And also, like I said, the ones in tensions probably didn't need to be doubled as much as the ones in compression, which we should have taken into account.
And then also down at the bottom where it's sheared from the roller, putting a member right there would probably help with that. Take some loads off our actual bridge deck.
So we have time for 2 questions?
Were you guys trying to like achieve reaching the like bending was before or the deflection before and actually was slow or is that something?
Was it a conscious design decision?
I think we sort of expected that with having the thick bridge deck and the thin members up top. We weren't exactly sure, but I feel like when we were in the process of designing, that's what we.
How much weight do y'all want to pull?
We don't remember. We haven't got, we haven't hit the data yet.
Exactly.
Yeah. It was, I think the strength to weight ratio is like 1.87, I think. I don't remember what the, 187, I mean, I don't remember what the,
I think it was like
what the thing was.
6,000.
Were you guys pretty intimidated when you showed up? There were guys with thicker members and stuff.
Yes.
Yeah.
We showed the.
She laughed at us.